Hi all. So I got a XML file from a student, and they're trying to figure out why they're getting some strange answers in their simulations, some large non-bonded energies. So we're going to go through this XML, and hopefully I'll help them get it straightened out. We'll see. All right. So let me quick do the screen share. So this is our basic XML format, and so if we go through it, it looks like we basically have defined all of the stuff. It doesn't look like anything's malformed, but if we are to take a look at, if we are to take a look at the console output from GOMC, let me make this a little bigger. So if we look at the console output, first thing first. So in GOMC, we have this thing called e-title. It gives you basically it's a column header. So it tells you what is in each column or what energy is in each column. And GOMC is kind of funny in this respect that it was originally written for an 80 column format, so everything lines up nice if you put this thing in 80 columns. So what are we looking at? So we have these different energy terms. We have this thing called intra-B. So that's intra-bonded interactions. That's things like bond stretching, bond bending, and torsional potentials. And if we go to the bottom of the log file and take a look, that we've got this really large bonded energy. So that suggests that the molecule is strained, that it wants to be somewhere, but it can't. And so let's take a look and let's see kind of what's going on with that. Okay. So my first thought when looking at all of this, if you go back to the XML file, so the XML file, we have to basically take all of the parameters from the original paper, and we got to put them in this XML format. And of course, there's a lot of places where things can get messed up. But the most likely place where things get messed up are in the torsions. So the first thing we're going to do today is look at the torsions and then see what we get. Okay. Okay, so let's quick take a look at the torsions. So here, what I've done is I've run the QM calculation. So I did what's called a relaxed potential energy scan, generated the dihedral and the rotational barrier, and I've compared that QM data with the original result that was in the paper, and you notice that there's a unit conversion in here to convert from Kelvin, which are the units were used in the original paper, to kcal per mole. So we've got all this on the same basis, and when we plot these up, then of course they match, which is good. That means that the people who wrote the paper, one of the authors was me, by the way, the people that wrote the paper didn't mess this up. But let's see what happens if we put the RB torsion form that was used in this XML into my spreadsheet, and let's see what we get. So give me a minute to put that back in there, and I'll be right back. Okay, so I am back, and let's take a look at what we've got. So I put the RB torsions into my spreadsheet. Here's my formula, and plotted them up. And let me put these side by side. So plotted them up, and this RB torsion that's in the XML does not look like the correct QM potential or the potential used by the paper. So let's come up with a new potential. Let's see, this is supposedly in kilojoule per mole, so I made a mistake. Let me put it in kcal per mole, 184. Still not gonna help. So we'll put this in the same unit so it doesn't confuse us. So anyway, so what we see is that when we look at these, that whatever the torsional potential was that was put in the XML has a minimum in the wrong place. And so we've got to fix that. So here we've got a minima at 0 and another minima right around 180. So the minimum at 180 is fine, but we should also have a minima at 60, which we don't have, and a maximum at 0. So something's wrong with this torsion. Let's go figure it out. Okay, so there is a direct conversion from RB torsions to periodic torsions. If you go to the GOMC manual, you can kind of dig this out. So if I have a periodic torsion like I had in the original paper, then I can do a conversion and turn that into an RB torsion. So we could do that, but I think that that's boring. I don't want to do that. So instead, what I'm going to do is I'm going to import my QM data that I generated earlier. So I just need to find my QM data. So I'm going to import those data. And we're going to refit the torsion ourselves. So I have these data. These came out of QM. We're just going to import into MATLAB. And I can get away with this. So I can fit torsions like this because in this case, there are no 1,4 Leonard-Jones or electrostatic interactions that are part of the torsion. So I can just fit the entire QM rotational barrier right to the, I can fit a torsional potential right to the QM data. I don't have to do anything fancy. All right, so I just had a little file format problem, but now I've got my data imported to MATLAB as a table. And so what we're going to do is first I have to do a little bit of a conversion here. So I'm going to make my X variable the angle, and I need to use this command table to array to take this table and put it into a vector, and my variable HFC 134A torsion 2 1 colon that should do it. Let's see what I get. Oops, I did mean that. Thank you, MATLAB. And let's hope it works. There we go. All right, so sorry, I just had this a little backwards. So what I'm doing is I'm basically taking that table and I'm grabbing the first column and stuffing it in a vector called X. And now we need to do the same thing for the Y. So now I need the, okay. So now these are in kcal per mole. The way MoSDeF works, it wants things in kilojoule per mole. So I'm going to make a little bit of a unit conversion. This is kcal per mole, like 4 times 4.184. So that should get us a unit conversion to kilojoule per mole, and the X I have to convert to let's see. See if this works. Okay, so now I have my X in pi language, and now I'm going to launch something called CF tool. All right, so now we're at CF tool. I got to grab my data. I got my X2, my Y2, and it's going to plot it up for us in a minute. And let's see what comes out of it. Okay, so these are our data. We have this, periodic torsional potential. If we take a look at it compared to our Excel spreadsheet, looks about the same. So that's our first sanity check to make sure we haven't got anything crazy going on. And now what we're going to do is we're going to do the curve fit. So we are going to put in a custom equation, and we're just going to start using, so we're going to have A times, and then this is going to be X minus pi, right? And it will automatically fit, and we're going to have to now just keep adding terms. This is going to be cosine X minus pi. Okay, not so good. Plus E times cosine X minus pi is the Q, sorry, square. Okay, not going so good. Plus D times Okay. A little strange. Let's see how this goes. Okay, hang on. Okay, so sorry, I had a mistake, and that mistake was in the first term, the A, that was incorrect. So I had to remove that X minus pi part. And you see now I've got this like very lovely match to the QM data. Now, we probably don't need all these terms. So what we can do is we can go through and we can take one away, and we can see what happens. Okay, so that was bad. We'll put that one back in. And let's take away the rest of these terms and see what happens. Okay, so that's bad. Because really what we want to do is we want to have a minimal, what's the minimal number of terms we need to have in here to make this thing go. So we don't need the fourth term. Let's try removing the third term. So we need that. Okay, so this looks like the minimal set of terms. I'll just try and pull this one out, see what happens. So we don't need that term either. Because there's no benefit to having a bunch of extra terms in your torsional potential if you don't need them. Anyway, so now we've done the refit, and we get, these are our constants that show up over here on the right. And if you check these numbers, is 8.954 and 27 and minus 36. These are quite a bit different than what's in the XML file. Okay, so probably that's our smoking gun. So this is what we have, and I'm just going to quick store this in my notebook. So put this over here with a picture of myself. And let's take a look. So what we're going to do now is we're going to take these parameters, we're going to put them in our spreadsheet, and we're going to see if we get the same torsional potential. So it seems like overkill, I know, but it's a good sanity check. Okay, so what I've done here is I have put in a new entry. This is our new RB fit, based on the MATLAB data, and I have put the formula in. So this is my formula, converted to kcal per mole to be consistent with the way my QM data are represented, and plotted it over here. And you'll see this is the gray curve here. Let me see if I can do chart tools, add chart element. Maybe we should add a legend. Okay, so the gray curve is our new RB torsion, and it matches the torsion from the original paper and the QM data. Therefore, we think that this should be good. And now we're going to take this new torsion and we're going to put it in our XML and run a simulation and see what we get. Okay, so let's bring up our XML. And so now, of course, I have to remember what all those terms are. Let's see if I can do this. So this is going to be 8.954. 0.954, okay. And our next one would be 7.42. The middle term is 0. Right, so I've got this, and then let's just do a sanity check here. So we got that one, that's the C0, this is a C1. C2 is 0, and then we have the other one. 2 is 0, and then we've got C3, that's going to be minus 35. Minus 35.67. These other two are 0. Let's see here. So we've got that. And we can use that same torsion for the other torsion. This is going to be HC. Okay, so now we've updated those torsions. Now what we're going to do is rebuild the system, run a simulation, and see what we get. Okay, so we're gonna use this thing called MoSDeF to build the system and build all the input files. I'm going to go through this file and I'm going to change a few of the things. So here we're saving an example of the XYZ coordinates to a mol2. Instead of sample.mol2, we should call that, we should give it a name. Okay. And then here, these, when we see this like underscore str, this is probably because if we have a complex script, we're going to call that, we're going to replace that with something else. But in this case, we're not. So let's just replace that with something else, and we'll call it let's see, what do we have here? Structure box 0. We'll just call this, how about this? Because this name and str is redundant. So now this way, we'll know what that file is if we look at it. And then here, force field file name. So again, we don't need this underscore file name.str. That's just redundant text. So we could just make this R134A underscore FF. So we know that that's the force field. And let's see, hopefully that's all we need to make things run. So I'm going to save that. I'm going to run it here. Let's hope it works. Okay, so looks like it built all of the files. Let's take a look. So now we've got initial box, right? So now we know what that is. It's got the PDB, the PSF. We've got R130A, 134A mol 2. So now we know what that is. We've got R134A FF. We know what that is. So we have all these things, and we don't have to think too hard about what they are because we've used, kind of a naming convention that makes sense. Okay, so now we're going to take this stuff, we're going to throw it into GOMC. Before we do, let's just look at the input file that was generated. So the input file that was generated, this controls GOMC. So it's got the right, you see it updated these entries correctly. So we're good to go. So we can run a simulation and hopefully we'll get something that makes sense now. So let's give it a shot. Okay, so for the purposes of debugging, I've copied all the files I need to make this thing run to a separate directory. Again, I'm just doing a quick test here. So obviously we wouldn't be doing this if we had like a complex workflow. But in this case, we don't. So anyway, let's give it a run. So we're going to do GOMC, CPU, NVT, and then we're going to use we're going to run on 2 CPUs. This is our control file, and we'll just pipe this to out.dat, and we'll run that, and we'll come back in a couple minutes and see what's happening with that. Okay, so welcome back, and let's take a look at our simulation and see what it's doing. So if we scroll down through, okay, a couple things we can take a look at. One is if we're looking at dihedral parameters, and we've got, let's see, so this is now been converted back to periodic torsions, and this is a number that is close to what I would expect to see. And now if we look at the energy, so remember we're looking at, let's see, 1, 2, 3, so third column, and let's see what we get. So we take a look at this. So now, here's our energy. That energy is now large and negative. Okay, now let's see what's happening there. Okay, so we've run this thing for about 100,000 steps, and now we've got a box of HFC 134A, and we can take a look at some of the molecules, and we'll just see this again. This is just a sanity check. So we're just going to grab one of the molecules. So I'll grab res ID 10 just for grins. So now I'll zoom in on it. So here's what I've got. Let me change the representation there so it's a little easier to see. Let's make that ball and stick, and we should always put this thing in orthographic mode. And so that is our HFC 134A molecule. And The geometry looks pretty good. Energy seem pretty reasonable. And if we were to, measure, so one of the things we can do is we can label, and in this case, let's label one of the dihedrals. So we'll book that one, this one, that one, and we'll grab that one. And what do we get for that? So that's got an angle of 56.67 degrees. And if we were to look at our spreadsheet, that puts us right in the minima, right at the bottom of the well, 56.67. So we can say that looks like at least that part of the model is pretty good. So anyway, so let me wrap up here. That's your basic torsional potential XML debugging. This is a fairly straightforward case. They're not always this straightforward, but hopefully this helps some people out there when they're trying to put molecules into XML format in the MoSDeF.